everyone, welcome to this session. So in this session, we're going to discuss some basic operations on tensors, which is somehow like the matrices. So we discuss summation, product, and transpose of a tensor. Then we discuss the dyadic product of two vectors, which creates a tensor. Then we have the horizontal and vertical dot products, and we discuss the trace of a tensor, identity tensor, which is the same as the identity matrix, and the inverse of a tensor. So let's get started with the summation of a tensor. So suppose you have two tensors here, and here I declare that if I write in capital letters, so the capital letters they denote the tensor, and if I write in a small letter, it denotes a vector. So A is a vector, and S and T are tensors. So this is distributive. So if you have the summation of two tensors, T plus S times A, which is a vector, then I can distribute this on T and S, so it is TA plus SA. And suppose if you have this equal to WA, where this W is basically the sum of T and S. So in indicial notation, I can write Wij is equal to EI T plus SIJ, EJ, this is dot, of course, here. So I can write this as EI dot, so TEJ plus, now it is time for SEI dot SEJ. And this becomes TIJ plus, this is nothing but TIJ, and this is nothing but SIJ. All right, and in matrix form, I can write W is equal to T plus S. Okay. Now, let's get to the product of two tensors. All right. In the product of two tensors, we have a definition. So we define all of these properties, all of these, let's say, basic operations based on, definitions here. So we define it as TS, so these are two tensors, times a vector is equal to T equal to T times SA. And also, we can write STA is equal to STA. So if you have TS, so if we have the product of two tensors IJ, so in indicial notation, we can write this as EI TS dot EJ, which is equal to EI dot T. So based on the definition we had here, we can write this as TSA, right? And here we can write this as EJ. And we already defined this SEJ previously in previous sessions as SE, for example, NJEN, for example. So from here, maybe it was better to just drag this here. All right. So you can write this as EI dot T. So instead of writing SEJ, we can write this as SNJEN and JEN. Okay, so now you can take out S and J. So this becomes S and J EI dot TEN. This is the same as TIN. S and J TIN. All right. We can also define in the same fashion STIJ is equal to EI dot STEJ, which is equal to EI dot S. So based on the definition here, so maybe I call this 1. So this is based on the definition from 1. It's based on the definition from 1. So you can write this as STEJ. So you can move the parentheses to TEJ. And TEJ is nothing but TEJ is equal to TNJEN is equal to, so maybe call this 2, this is 2, this is 3, and this is 3. All right, so this is EI dot S, this is TNJEN. So I can take out TN here. So TN EI dot SEN, which is nothing but SIN. So TNJ SIN. Which of course this can be written as SIN so it doesn't make a difference if you just rewrite them or rewrite them in a way that S comes first or T comes first or any of them comes second, so you can easily swap them. All right, so in tensorial form, we can write TS is equal to TS. And also ST is equal to S times T. But you have to know that ST or is not equal to TS. You can just prove this by providing a, an example and reject everything. All right. So overall, ST is not equal to TS. So if we have, for example, we can also expand this to, for example, to 3, let's say, tensors. So if you have a tensor like T, S, and V, and you time all of these, this is equivalent to, let's say, T. So you can just take T out. So this becomes S. This is SVA, because you can treat this as, for example, a tensor like A, and this is the same as TSA we had before. So you can take this here. So this is ATA, TAA, which is the capital A, I mean. And this is also, you can also take, treat these SV as we had TS before. So you can say that this is T and S, and you put VA here. So this is all about the product of two tensors. And of course, if you have, for example, if you have T3, this means T, T, T. If you have T2, it means T, T. Or if you have T, for example, N, so T to N, so it means that you have like T, 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 n times multiplied together. So next we have the transpose of a tensor. So according to the definition which is provided for the transpose of a tensor, if you have, let's say, two vectors a dot a and b, so we have the tensor T A dot TB is equal to B dot T transpose A. This is the definition for the transpose. And also, if we have, for example, EI dot TEJ, so we define according to this definition here. Let's say this is 1, 2, 3. According to 4. So according to 4, you can write EITEIJ. TEJ is EJ dot T transpose EI. So you can simply write TIJ is equal to TJI transpose. And in tensorial, in a matrix form, you have T transpose is equal to T transpose here. All right. So you should also know that if you have, for example, a tensor like T transpose and you transpose it again, so you get T. And if you have a series of, let's say, tensors of A, B, up until, for example, Z, for example, transpose, so it is equal to Z transpose, B transpose, A transpose. Next, we discuss the dyadic product. This is rather a new, this is a rather new concept. You might not have any second thought about dyadic product. So actually, this comes to two vectors. So we define this as AB C is equal to AB dot C. This is the definition of the dyadic, and here the book used the notation of AB only, but here to distinguish I use this symbol here. So I have a circle and I have a cross in it, so this means dyadic. And why this definition is true, so if you have two vectors like here, so you have A of, let's say, 3 by 1. Then you have B, which is 1 by 3. So this gives a tensor of, let's say, 3 by 3. And if you have a vector of 3 by 1, this finally gives you a 3 by 1 vector. And this is A, which is 3 by 1. And you have B dot C, which is a scalar, or zero order tensor. So these are equivalent. That's why this definition is true. We also have another definition, but or let's write it like this: A B C is equal to A B dot C. Okay, this is the definition. So let's suppose that you have a dyad B, alpha C plus beta D. So you can expand this based on this definition here. So based on 5, you can write, okay, this is like C. So this is A, so B dot C, which is B dot alpha C plus beta D. This is like C here in this definition here at this C. Okay, so we expand this a dot, so this becomes a b dot alpha c. So I can take alpha out because alpha and beta are scalars. So alpha bc plus, oh sorry, dot plus, this is b dot beta d, b takes out. So you have b dot d. And here you can also rewrite this as alpha a b dot c plus beta a b dot d. And that's it. So we have this defined based on 5. Again, based on 5, this is nothing but a dyad bc. So it is alpha a dyad bc plus beta, and this is a dyad b times d. So a dyad b times d. And you also have to remember that a dyad b is not equal to b dyad a. This is way too important. All right, so we can also define the components of a tensor based on the dyadic product. So redefine, or maybe it's define, maybe it's better. Define the a tensor. Define a tensor using dyadic product. And it is as simple as that. So if you have Tij, you can write it as EI dot Tej is equal to, let's say, E. So this can be written as, TEI, and you can write this T as the, let's say, the product of two vectors. We already talked about this. So let's say that we have A and B, so EJ. And based on the definition here, so it's a dyad BEJ, because this gives a tensor. This gives a tensor, which is the same as T. So based on the definition from 5, here you can write this A B dot C. So you can write EI, and you can write this as A dot A B dot EJ, and this is nothing but AEI, and B dot EJ is nothing but BJ, and this is AI. So it is AI BJ. So it is so Tij is equal to AI BJ. So you can basically write T as the product of two vectors. And here I have to mention that I made this assumption. So we assume I just jumped ahead. We assume that T is equal to A dyad B. So we assume something like this, and then we finally get this. So any tensor can be written as the dyadic of two, let's say, two vectors. So it means that if you have a tensor like T, this is equal to A1, A2, and A3, for example, here, and you have B1, B2, and B3. So if you time A1, B1, A1, B2, A1, B3, A2, B1, A2, B2, A2, B3, you have A3, B1, you have A3, B2, and you have A3, B3. All right. We can also expand this to, let's say to the unit vectors. So EI dyad E1 dyad E2 is equal to, sorry, this is 1, 0, 0, this is 0, 1, 0. So this is 0, this is 1, 0, 0, 0, 0. These are all 0. So you can see that this is equal to let's say the delta ij here, or E1 dyad E1 is nothing but the dyad of these two, which is 1, 0, 0. The rest are 0. So you can see that this is equal to delta 1, 1. And so now we can define T as equal to the tensor T, since we brought these, this dyadic product here as, for example, T11 E1 1, because we already proved that it is the dyadic of two vectors. So all the let's say all the components can be written in this form, this fashion. So this is, oh sorry, plus T12 E1 E2 plus the rest, which is equal to Tij Ei Ej, which is basically Ei dyad Ej. So, for example, if you want to find the first component of T, let's say T11, so it is basically T11 E1 dyad E1, and this one is also T12 E1 dyad E2. So basically, if you want to find T11, so you need to find E1 dyad E1, which is basically this tensor here, and you time the component you want, the quantity. So it has a quantity here. So if you time T11 time this tensor, it will give you finally T11 component. So let's get to the trace of a tensor. All right. So we define the trace of a tensor as the trace somehow similar to the trace of the matrix. So we have trace of T plus S is equal to the trace of T plus trace of S. So it is somehow like a linear transformation we had. And we also have the trace of a scalar field times a tensor is equal to alpha trace of T. And if you have the trace of A dyad B, which is the same as, the trace of T is equal to A dot B. Because when we say A dot B, we are basically talking about the let's say, the diagonal components here, A1, B1, A2, B2, A3, B3 here. So that's why we use this kind of, you know, definition here, and we call this 6. Yes, 6, true. All right, so if we have the trace of a tensor like T, so we define it as trace of Tijei dyad Ej. So the book used Tijei, but this is the dyad, which is missed here. So I use this kind of notation. Again, I emphasize. So I can take out this Tij here. So I can say the trace of Ei dyad Ej. And here we already mentioned that 6.1 says that this is equal to A dot B. So this is Ei dot Ej. So this is Tij. Let's say ei dot ej, and this ei dot ej is nothing but delta ij, and for this to be meaningful, we say I is equal to j, so this is t I, or for example, this is equal to t j j. So we define the trace of a tensor as Tii or Tjj is equal to T11 plus T22 plus T33, which is basically the summation of all the diagonal components. I've already mentioned this here. Diagonal components, the summation of the diagonal components. All right. There's also another property you have to know. So the trace of T transpose is equal to the trace of T. Why? Because during the the definition of the transpose, we already mentioned that if you have something like T1, T12, T13, T22, T2, oh sorry, this is 21, 22, 23, 3, 1, 3, 2, and this is 3, 3. This is T. So if you transpose it, so this basically becomes, so you swap the rows and vectors. So T11 stays on its place. So this becomes T21, T31. So all these goes here. And we have T12, T22 stays on its place. So we have T, oh sorry, 3, 2, and this is T13, 2, 3, and this is T33. So you see that these diagonal, which is the trace of both T and T transpose, the summation of the diagonal components remains the same. So that's why we say that the transpose of T transpose is the same as the trace of the tensor T. All right. Now, we would like to know the trace of, for example, let's say A times B. So we have two tensors and we want to know what is the trace of the product of two tensors. So let's suppose that B is equal to C. So C is equal to AB. So if I write it in the initial notation, I have Cij is equal to AIM BMJ. And finally, if I define the trace of C, so the trace of C is equal to CII. So this means that it is equal to IMBMI. Similarly, I have the trace of A, B, C, and D is equal to A, I, M, for example, B, M, N, C, N, J, and D, J, I. Why? Because I can equal this to E, and the trace of E is nothing but E, I, for example. And finally, this gives EII. All right. So let's get to the next topic, which is the identity tensor. Identity tensor. So we define this as similar to, let's say, the identity matrix. If we have I, so I is the identity matrix, so we call it I here. And we use this definition that if we multiply I with a vector, it becomes the same as the vector. So if you have, we call this 7, and if you have I times a tensor, so it gives the same tensor here. So it becomes T again. And this is somehow commutative, so you can write Ti is equal to It is equal to T. And we define I as 1 0 0 0 1 0 0 0 1. So all the diagonal components are equal to 1 and the rest of diagonals are 0. So yes, that's it. And if you have, for example, two tensors like S and T equal to I, so that means S is equal to T inverse. So it is the inverse of S is the inverse of so S is equal to T inverse. So in let's say in matrix form, if you have T times T inverse is equal to T inverse times T is equal to the identity. And we also have T inverse transpose is equal to T transpose inverse. So it doesn't change anything. And we also have this property here. 1, 2, and 3. So this is 4. Here they says that if you have T in TS, the product of two tensors, inverse is equal to somehow like somehow similar to the transpose. This is S inverse T inverse. So if you have, for example, you know, a series of A, B, C, D, A, B, C, and it goes to D inverse, it is D inverse, the rest, C inverse, B inverse, and A inverse. And also, if you have TA, T times A is equal to B, then you can multiply each side by T inverse. So this becomes T inverse TA is equal to T inverse B. And you have to pay special attention here that if you put this here, T inverse, you have to put it before B. You can't put it right here. This is not allowed due to the dimension problems in multiplication. So this becomes actually I, so this is equal to IA, which is the same as, you know, oh, sorry, T inverse B, which is the same as A. So A is equal to T inverse B. And I guess I have to change this to the title to and inverse of a tensor. Right. Okay, so here is an important property. I read it from the book. So if you have, for example, two, let's say, two vectors A and B, and if you transform vector A into B using this, let's say, tensor T here, so if T is invertible, Therefore, you have one-to-one mapping. So there is only one transformation or mapping or tensor that can transform A into B. But if T is not, let's say, inversible, you can't inverse it. It is singular, for example. We had the same concept in matrix algebra. So if the determinant of let's say T is equal to 0, therefore you cannot invert it. So if it is not invertible, therefore there might be several or infinite number, or I don't know, more than one, let's say, transformation matrix that can transform A into B. So let's recap this as TA is equal to B. So you have to notice here that if T is invertible, so you can invert it. Therefore, there is a 1-to-1 mapping T that can transform A into B. If T is not invertible, so the depth of T is 0 or is singular, therefore there is more than one mapping like T that transforms A into B. And this is actually shown here in example 2.14.2. And I guess this is quite important to know, so I will solve it again here. So it says that if you have, let's say, C diad D is a tensor, so T is equal to C diad D, then obtain the determinant of T. So we can write C is equal to C1, C2, C3, diad D1, D2, D3, which is equal to C1, D1, C1, D2, C1, D3. This is C2, D1, C2, D2, C2, D3. And this is C3, D1, C3, D2, and this is C3, D3. So if we take the determinant of T, so I just use the SymPy tool here. So I imported the SymPy tool here, and I said that I have these, symbols defined here in this line. And in line 3, I defined C and D as row vectors here. And finally, I have T as C times, the transpose of D, because now C is a column vector and this is a row vector. So basically, the T is a matrix at 3 by 3, let's say tensor, but it is written in matrix form, and the determinant of T is equal to 0. You can also do this by hand, so this gives 0. And in the second part, so it's the A part. In the second part, so it says that if you have T, A is equal to B, then T, A plus H is equal to B, where h is orthogonal to let's say the vector d. So that means h dot d is equal to 0. Their dot product is 0. So here we're gonna say that if you have, we're gonna actually discuss this topic here, that if t is invertible, there's only 1-to-1 mapping. But if t is not invertible, like the case we had here, the determinant is 0, therefore we have more than one mapping that can transform A into B. So we start from t times A plus h here. So we also assume that it is stated that t is the product of the dyadic product of C and D. So say C dyad D, A plus H here. And here we say that this is based on the property number 5 here. So a dyad B, C here is A, B dot C. So based on 5, this is C dyad D, and we have A here. Oh, sorry, this is C. This is like the vector C in A dyad B. C is equal to A, B dot C. So from here, so A dyad B, C dyad, this is C, so this becomes A, which is C. This is B dot C, so this is D dot A plus H. Good. So we convert it into this. I can write this as C D dot A plus D dot H. And from here, from this assumption, like I call it this Black square. So from Black square, D dot H is equal to 0. So I can write this as C D dot A. So this is equal to, based on the property of 5, this is equal to D dyad A C. Or I guess that I made a mistake maybe. So A dyad B, C is equal to C, sorry, A, B dot C. So this is like D dot A. So I have to write it like C dyad D A. True. And C dyad, let's say D is nothing but T. So this is TA, which is equal to, again, B, according to here. So TA is equal to B. Therefore, we can say for any value of H, we get this transformation. So there is more than one transformation that can transform A into B. And the next topic is the horizontal and vertical, let's say vertical dot products. So I just bring the definition, and you have to remember that these are not actually included in the book. So, but you might come across in some scientific papers or literature. So if we define f, so if we have f, a tensor, so we use the double dot product in the horizontal, and G is another tensor. We define this as f I j g j I. So it is like, you know, u times 1 2 the component 1, 2 with 2, 1 component of G. And this is the horizontal dot product. And we have this F double dot G in the vertical form is Fij G Ij. This might look a bit weird. So it is like, 1, 2 component times 1, 2 component plus, for example, 1, 3 component of F times G1, 3 component, and this is the vertical dot product. And you have to remember that these follow the summation convention. So do not write it like F double dot G is equal to F12, F11, G11 plus F12, G12 plus. So you have to put G, and do not write it like you completely forget this as F11, G11. F13, G13 plus F14, sorry, 21, G21 plus the rest of the terms here. And this is here for F double dot, sorry, for F double horizontal double product is F double dot G is F11 G11 plus F12 G21 plus F13 G31 plus F21 G12 plus the rest of the terms.